Hello, I'm Anneke Avery. I'm a junior at Calvin University. Today, I will be presenting the second part of a three-part series on the evolution of contact binary star systems. A contact binary star is a pair of stars orbiting so closely that they share a common atmosphere. The first presentation described how we use the MESA code to compute the evolution of such systems. In this presentation, I will show how our models for the formation of these systems yield the input parameters for our computations. Our calculations produce distinctive properties for contact binary systems nearing death that we can use to observationally test our ideas. Contact binary systems start out as a detached binary with a third companion, as depicted here. The presence of a third body exchanges angular momentum between the pair and the third companion. The binary has the same amount of energy, but less angular momentum. This causes the binary orbit to stretch, increasing its eccentricity without changing the semi-major axis. This initiates tidal friction, which takes energy away without changing the angular momentum. So tidal friction takes the large eccentric orbit and makes it into a smaller circular orbit. And then we repeat. This cycle of third body oscillations increasing the eccentricity and tides attempting to recircularize causes the binary orbit to get smaller and smaller. This cycle stops when the precession rate, which increases for smaller orbits, equals the third body oscillation rate. The precession rate also increases for smaller mass stars, which is what this graph shows. If the precession rate is too fast, then this process doesn't work and we can't form a contact binary. This rules out primary stars smaller than 0.9 solar masses. Tides enforce synchronous rotation, so as the orbit gets smaller, the rotation gets faster. We needed the processes from the previous slide to get to a small orbit because magnetic braking works better with faster rotation. What does magnetic braking do? Magnetic field lines rotate rigidly with stars. Mass lost along the field lines causes a loss in angular momentum, which drives the stars to spiral in even more. So if third body interactions can get us to a smaller orbit with faster rotation, magnetic braking can kick in and drive the stars closer until they reach contact. But in order to do this, the star requires a magnetic field, which means it needs an inner convective region. The gray part on the left of the graph shows that this rules out stars bigger than 1.3 solar masses. We saw that third body interactions and magnetic braking make the orbit keep getting smaller. This stops when the primary star fills the Roche lobe. The shape of the Roche lobe is fixed by the mass ratio of the binary, but the size of it depends on the orbit size. We saw that the mass range is quite narrow and about the size of the Sun. You can imagine that the yellow circle is the Sun and that this is the Roche lobe for it. As the formation mechanisms make the orbit smaller, the Roche lobe gets smaller until it is the size of the primary star, and a contact binary system is born. All of this means it takes time to form a system. Therefore, we started our evolutionary calculations at an age of 1 billion years. From here, we take the system, which looks like something you see on the top, and evolve it by conservation of mass and angular momentum, as described in the first talk, until it looks like what's on the bottom. Here we reach a critical mass ratio where the rotational angular momentum of the big star is a quarter of the total angular momentum of the system. This is where we stopped our evolutionary calculations. At this point, the big star needs more angular momentum to stay synchronous with the orbit. The companion doesn't have much mass left to give to the big star, so it moves in. This smaller orbit rotates faster, requiring even more angular momentum. This is a runaway effect, and the stars start spiraling together rapidly. These are the graphs of mass ratio versus period and temperature versus age for a primary star of 1 solar mass and a range of mass ratios. These graphs show some notable final conditions. We end up with a range of long periods, about 0.7 to 1.6 days, a narrow range of mass ratio, which is much smaller than the initial mass ratio, and small temperatures, which drop down to 5,000 right at the end. We have found 7 high period derivative stars, meaning that they are in the final stage of spiraling in, that are within this long period range. We are proposing to observe the mass ratio and temperature for these stars on a large telescope to compare with our specific predictions for these values. This will be a great test of our evolutionary calculations. Thank you so much for listening to my presentation. I look forward to any questions that you may have.